Hello everyone. Today we are gonna continue together the PN junction and diode. So in the last class, let me minimize the screen. In the last class, we discussed together the meaning of the PN junction and how the PN junction can be forward biased or reverse biased. I'm gonna review this very quick also in another slide. And we discussed the meaning of the barrier. So the barrier volt is the volt required in order to break the depletion region in order to move electrons from a junction to through the PN junction itself from P to N or N to P, whatever current or electrons. And we solved an example, and also we discussed the capacitance of the PN junction, and we discussed together according to the relation of the capacitor. So if the distance increases, so the capacitance will be uh, uh, increased. So the relation between C and D are inverse relation. Increasing distance, capacitance decrease, or decreasing distance, capacitance increase. So in the depletion region in the forward bias, we know that for forward bias, let me write this down here. So we have the two cases now. Let's start with the forward bias. So in case of forward bias means this is the PN junction, this is P, this is N. So connect P to plus supply, connect N to negative supply. This is the forward biasing. So forward biasing means the positive charge here will uh, will be opposite to the positive or whole charges here. So it will make the holes to move in this direction. And the same is also for the negative charge. Negative charge with the negative of the supply will move the electrons here to that side, which means it's going to make the depletion region decreases. So the depletion region will decrease here. So this means distance decrease. This is in case of forward bias. And decreasing distance means also the capacitance increase and the resistance decrease. The resistance decrease means current will flow. So this is the concept now of the forward bias. In case of reverse bias, so reverse bias means this is P, this is N. So P is connected to negative, N is connected to positive. So here the positive holes will be interacted or moving toward the negative, okay, and the negative charges in the N-type material will move toward the positive. So this means the depletion region itself will increase. So this means the distance increase, so the capacitance will decrease, and at the same time the resistance will increase. If you would like to know some numbers, guys, so the semiconductor material can have resistances. So resistance could be in milliohms. Okay, we have some semiconductor materials now that the equivalent resistance or the PN junction resistance can reach to 0.1 milliohm, so very small value of resistance. And here, in case of the reverse bias, the resistance can go to hundreds or giga ohm, hundreds of mega ohm or giga ohm. So it's like completely like isolation, which means by the end, the high current can flow here. So I will be flowing with high value, but here the current is going to be only I leakage. So the leakage current, which is the saturation current, which is in like pico ampere or nano ampere, so very small value of current. So this is the concept now of the forward biasing and reverse biasing that we discussed in the last class. And here we mention how to operate or start moving electrons through the junction. We mentioned that the volt has to be greater than the barrier. And we mentioned that the barrier, according to the semiconductor material, it could be 0.4 volt to 0.8 volt, for instance. And we will see that, guys, in some data sheets of some power or electronics component based on the PN junction. And we also knew the relation of currents and we define every variable. So ID is the junction current, or let's say for diode, so this is going to be the diode current. IS is the saturation current or leakage current, and we define the different terms here also. So we have the as we mentioned, IS is in 10 to power minus 12, 10 to power minus 18, very small value of current. And VT is the thermal volt, which is 0.026 at 300 degree Kelvin. And we mentioned that N is constant. It can be vary from 1 to 2. If it is not given, we'll assume all of the time it's 1. And this is the relation of current now. So this is simply the diode current. And we solved actually a problem here. If we applied positive 0.7 volt or negative 0.7 volt to our PN junction, how much current is going to flow? So we could find that at 0.7, the current flow is gonna be 4.93 milliampere. This is in case of forward bias. So this is in case of forward bias. And in case of reverse bias, we substitute here by V equals minus 0.7, and we substitute in the relation, and we found out that the the diode current is 10 to power minus 14, which is the saturation current. Saturation current here, guys, it doesn't mean the greatest value. No, here the saturation current refers to the leakage current in the semiconductor material. Then we mentioned that the first element in electronics we will discuss here, guys, is the diode. So the PN junction diode. Diode is the first element. It's used in electronics and in power electronics as well. So you can find some diodes with very small value of current, starting in current in milliampere. And in power application, you can find some diodes reach to kiloamperes. So these are the ranges of diode we have in our life. And we will see a lot of different types of diodes in our classes this semester. So what the symbol of diode? The symbol of diode, as you can see here, guys. So this is the symbol. The positive side is this one and called anode. And the negative side is the other side here, and this is called cathode. So if we connect positive, negative, as you can see here, this means the diode is forward biased and we expect a current to flow. For that, guys, in order to turn on the diode, we mentioned that VD has to be greater than V barrier, which is semiconductor dependent, could be 0.4, 0.7 according to the material. And once we have VD greater than V barrier, so this means the current will flow. So for instance, guys, current starting flowing here from this point. So all of this here, all of these places are very little current, which is the saturation current, very small value. And once you have V at this point here, VD greater than V barrier, so a current will start flowing, as you can see. Here, this is a small diode current. As you can see, the current range is in milliampere. But later on, we will see higher values of current. What about the reverse biasing? Reverse biasing means connect negative to anode and the positive to cathode. So this is here in forward biasing region, guys. This is here in reverse biasing region. So if this is our diode, so here this is negative and this is positive. So this is a reverse, and in forward this is our diode, and this is positive and this is negative. What do we expect? We expect to have very small currents, but it's not going to be moving to infinity, guys. There is a certain limit, and we will discuss it in the coming slides. Okay, so at a certain point, something will happen here. Okay, we will discuss it in other slides. So this is called the reverse biasing and forward biasing. And again, the reverse biasing, we will continue discussing the remaining characteristic of the reverse biasing in the other slides. Here, so what is happening after reaching to a certain level of volt? Actually, we have what's called the breakdown volt. What's the meaning of breakdown? Breakdown means the diode will be damaged. Why the diode will be damaged? Because the volt will be relatively high, and this volt will make like braking for our junction. But braking for our junction, not to flow current, it's gonna break it forever, which means the diode will damage if we reach to this value. So we shouldn't operate the diode at this value. Here we have two different values for two different diodes. And here, as you can see, guys, this in case of high doped and this case of low doped material. Okay, so it depends on the doping material in our diode. Okay, so this is now the complete characteristic. You don't need to draw two characteristics, so one characteristic is sufficient. So let me draw here the characteristic like that. So this is gonna be the plus or forward biasing, and in the reverse biasing, I'm gonna draw it like that. And I have to define the terms. So this is V, this is I, here forward, here reverse, and I should mention that this is V breakdown. So this is a breakdown volt, and here I can say this is here V turn on, which is sometimes we refer it as V gamma. Okay, so this is the turn on volt. Okay, guys, so this is called the IV characteristic of our diode. IV characteristic of our diode. So this is IV characteristic. So characteristic, we write characteristic like that, C/C. So this is the IV characteristic of a PN junction diode. Okay, now we are familiar what is the shape of the voltage and current in case of forward biasing and reverse biasing. Let's see something else important called the static characteristic. So what the static characteristic? So what we have here is the dynamic characteristic. So this characteristic is called dynamic or IV characteristic. Let's see another characteristic which is referring to the static characteristic or transient. What the transient? Transient means the interval of conversion from a state to another state. So, for instance, here we will discuss the switching transient in turn off, which means the diode was on in the beginning and then we turned the diode off. How the diode will be turned off? How the diode will be turned on? We will discuss more in deep now. So we mentioned that in order to have diode on, you have to have V diode greater than V barrier. Okay, so this is the condition to turn on a diode. But what's the condition to turn off? So in order to turn a diode off, we have actually two conditions. Sorry, we have either volt should be reversed, but we have another condition has to be achieved, which is I should reach to 0 or less than a value called latching current. So the diode will not be turned off if there is a current flow in the diode itself, even if the volt is reversed across this diode. And we will see this later on in our class. So let's see now the performance, guys, in case of turning off a diode. When you turn off a diode, actually the current is not gonna flow. Sorry, the current is not gonna turn it on off completely or instantaneously at 0 value. What will happen is, if the current is flowing due to any external supply volt, higher external supply volt in reverse biasing, and sometimes, guys, we call it commutation. So commutation means turning off an element. So what happened is the electrons are already flowing in a very high speed. If you're gonna turn off a diode, the electrons are not gonna stop immediately. So can you imagine now, for instance, if you are driving a car, so I would like to stop the car, so I cannot stop the car at 0 seconds. So the car, in order to stop a car, the car will be slowing down until reaching 0. So this is the same what's happening in any physical element. So electrons are moving in a very fast speed. So what will happen is the current is gonna move from positive to negative and then decay until reaching zero. This period, guys, is called reverse recovery. Reverse recovery. Okay, and the charge of this period called reverse recovery charge. We will see this together in the data sheet. Okay, so let's read together the comments we have here. So the reverse current IR is approximately constant for T greater than 0 and less than Ts. What is Ts? As you can see here, guys, Ts is referred to the settling time, where Ts is the storage time. Okay, sorry. So he refers here as storage time. Okay, so Ts here is the storage time. Okay, nice. So when the diode will be completely off at this point here, when the current reaches to zero. But we have another term here called falling time. Falling time means the current is moving from a certain value to around 0.1 or 10% of the maximum reverse current we have here. So this is called the fall time. Okay, so these are the two times we have here: storage time and the turn off time. We call it storage time, guys, by the way, because it's like charging a current in the opposite direction. So you store the charges in the junction of the diode, and junction means the capacitance of the diode. So since the PN junction has a capacitance, so this capacitance is going to be charged in the opposite direction. So we call it TS. So this is the storage time. Okay, and then since you don't have more sources because the current is turned to, or the supply is turned to zero here, so this is gonna make a decay for the charges until reaching zero. So this is called the falling time. What the turn off time now? Turn off time is the total time, Ts plus Tf. Okay, so this is called the turn off time. What about turning on? So turning on transient occurs when a diode is switched from off to on, which can be initiated by applying a forward biasing current pulse. So firstly, we apply a forward current pulse or apply positive volt across the diode. The transient turn on time is the time required to establish the forward bias minority carrier distribution. So this is actually the turn on time. The time required in order to install the minority carriers distributed in the material in order to allow a current to flow. So this is called the turn on time. Although the turn on time of a PN junction diode is not zero, zero is the ideal case, okay? So practically it's not zero, it is usually less than the transient turn off time. Why? Why we don't have long time for turn on like what we have in turn off? Because of the reverse recovery. Because of the reverse recovery. Okay, guys. So this is just a quick discussion about the transient performance of a PN junction diode. Now we need to drive the equations of current. Simply, if you have like two switches now, or manual switch with two ways. So in the first position here, before t equals 0, so at this case number 1, so the plus sign of the battery is connected to the anode of our diode. So this means it's forward bias. How can we calculate the IF, the forward current? Simply, if you have a look here, so we can say now the current IF equals this volt minus any other volt in the circuit divide the total resistance. So we can replace these diode, guys, by means of resistance and battery. So let's replace the diode together. So the diode, the PN junction, can be replaced like that. We have a battery. This is called the VD. This is a plus sign and this is a minus sign. Plus sign in the side of the anode and minus sign in the side of the cathode. And then you have a resistance of the diode. So here in this equation, he called the resistance of diode as R, or even he neglected here the resistance of the diode in this equation, but practically you should have what's called R on, R diode on. Okay, so if you replace the circuit by the equivalent circuit of your diode, so you have here, for instance, RF, and you have a source volt here, and you need to get the current due to forward. So this is called V forward here. So I can say, guys, if I apply Kirchhoff here, so I can say I forward equals V forward minus VD or V diode divide total resistance of the circuit, which is going to be RF plus R on. So this is now the forward current. Here in the equation, as you can see, he neglected the resistance of the diode, no problem. But if the resistance of diode is given, so this is going to be the exact solution. This is in case of forward biasing. In case of reverse biasing, what will happen is we will connect at T equals 0, so the switch will move here. So this means the current, firstly, the current will be reversed. Secondly, the value of the current is going to be now minus VR minus VD divide total resistance again. Okay, so this is again, here we neglected the resistance of our diode and we consider only the external resistance. Okay, guys, so this is how can we make calculations for diode in case of forward biasing or reverse biasing. Now, we discussed the characteristic of the PN junction diode. But what is the ideal case? So, ideal case, firstly, guys, let's define the ideal. Ideal for anything in life means it's something that cannot happen. Nothing is ideal in our life. So ideal diode model means there is no ideal diode in the world. But what is the most preferred characteristic of a diode? This is called the ideal. We cannot reach to the ideal, but what is the most or the best performance of a PN junction diode? The best performance is going to be in case of turning off, the current should be 0. And in case of turning on, the current should be ID and you don't have a resistance. But in this case, if you don't have a resistance, this means V diode is going to be 0 because you don't have resistance here. So I times 0 equals 0. So the ideal case in case of turn off, VD is less than 0 and ID equals 0. VD is less than 0 because it could be in reverse biasing. Okay. And in the positive or sorry, forward biasing, the ideal case is ID is a value greater than 0 and VD equals 0. So if you draw this characteristic, you will end up with this shape. So this is the ideal case in case of forward or conducting state, and this is the ideal case in case of reverse state. Okay, so this is the ideal diode model. Now, let's see how the current is flowing in case if we have AC supply. I need to discuss more in deep here, guys, in this point, because this is very important application. We use it in our life. You know, guys, all of us are using power supplies. What power supply is? Power supply is nothing but converting AC supply into a DC. For instance, if you have your computer, for instance, computer needs DC supply, and what you have at home is AC supply. So in order to supply your computer, you need to convert AC to DC. How can we do that? We need a power supply. One part of the power supply is called rectifier. The main element of rectifier is diode, if it is uncontrolled rectifier. So diode is one of the important elements. We use it in power supplies. How the diode is going to work if we have AC source and our load is only resistance. For sure, guys, our load can be any type of load. It can be resistance, it can be inductance, it can be capacitance, it can be RL, it can be RC, it can be RLC, it can be something else like back EMF along with the RL, like motors, for instance. So all of these are different types of load we may have with our diode. Let's start with a simple example here. Just we have a resistance. Now, we said when the diode will be turned on, the diode will be turned on if V anode minus V cathode is greater than V barrier. Let me write down this here. So if V anode minus V cathode, which is nothing but VD. So this is VD, V anode minus V cathode. If this volt is greater than V barrier, so this means the diode will be turned on. And if the diode is turned on, ideally it's going to be a short circuit. So this means the output volt on the resistance will be the same as the supply volt. So if this is V input, sinusoidal waveform, as you can see, we expect that once V became greater than 0, or let's say greater than 0 in ideal case, but in practical case, greater than V barrier, which is 0.4 for instance, so a current will start flowing. And if a current starts flowing here, the volt across this resistance will be the same as the V input. So this is what's going to happen in this positive half cycle. So this is a turn on. As you can see, guys, here at this point, what is the current value? This is the voltage curve. We didn't draw the current curve. So this is our load. Our load means for any resistance, guys, you know that I equals V divided R. This is RMS, or instantaneously we can say I equals V divided R. So this means if I would like to draw the current waveform, let me change the pointer color here. So if I would like to draw the current waveform here, so assume R, guys, here equals 0.5 ohm. So if R equals 0.5 ohm, so this means I equals V divided 0.5. So this is going to be 2 times V. This is assumption. Assume we have a resistance equals 0.5 ohm. So in this case, the current is going to be twice of the voltage magnitude. If I would like to draw now this curve of current, so I'm expecting that the current is going to start here, increase, and then it will decrease at this point. So sorry, this is a freehand sketch. So the current reaches 0 at angle pi. Angle pi means 180 degrees. So this means, guys, current drops to 0 at this instant. If you remember, in the previous slide, we mentioned that the condition to turn off a diode is current reach to 0. So once current reach to 0 here, this means the diode will be turned off. Diode off means I equals 0. So you don't have any volt across this resistance because 0 times R equals 0. So the volt will be 0 at this interval until having the supply turn it to positive again, and it will move again by the same shape. So this is, guys, I of omega t. Omega t, because here we have this axis omega t angle. It's not only time. So this is simply, guys, the operation of a diode if we applied an AC supply. If we applied DC supply, so if it is forward biased, so this means the current will flow. If it is reverse biased, so the current will not flow according to the value of the applied volt. Okay, so this is what we have for the part of if we applied an AC supply to our diode. Let's make analysis, but DC analysis, not AC analysis now. What's the meaning of DC analysis? DC analysis means we are going to assume that the supply is DC. AC analysis means the supply is AC. So what do we have in our life? We have both. And also, guys, the supply is not ideal, which means the supply itself, it could have AC and DC together. So if we go back just one slide, this supply here is AC supply. So AC supply means it's vary between positive and negative, and ideal AC supply has the plus and minus area equal. So this is ideal AC supply. Ideal DC supply means constant value forever. This is the ideal DC supply. But you may have a mixed supply. Mixed means you have AC and DC added together. For that, guys, we discuss in other courses what's called the Fourier series. So Fourier series, for any waveform, you will have AC component and DC component. DC component means the DC part of the waveform. AC component means the AC parts in a waveform. And I said AC parts because we have different frequency values. So it could be fundamental frequency, it could be second order, it could be third order, and so on. So this is what's called Fourier series. I think you will learn that in signals and systems in another class. Okay, so let's now see the performance of a PN junction diode in case of the DC analysis. So assume, guys, here we have a power supply, we have a resistance, and this is our diode. So this is the DC source, and we mentioned that the current is going to be flow if the VPS is greater than VD. Now, whatever the value of VPS, I would like to calculate ID. So I can say, guys, apply Kirchhoff voltage law to this circuit. So simply, VPS equals I times R plus VD. I know, guys, all of you like now became expert in electrical circuits for sure, but let me just make a quick revision with you if I would like to draw or to write any equation for a circuit. So let's say summation voltage sources equals summation voltage drops. So voltage sources, we have just one voltage source here, which is VPS. If a current is flowing in this direction, so this current is going to make a polarity in this direction, and the voltage magnitude will be R times ID. Here also, we have already a polarity for the V diode. This is plus and this is minus. So we can say now VPS equals R times ID plus VD. Okay, so this is Kirchhoff current law, Kirchhoff voltage law and Kirchhoff current law both. So we applied firstly current. We don't have branches here, just one current, and we applied Kirchhoff voltage law there. So I'd like to get ID, so simply we can move VD to the other side in negative sign, and then divide the other side by R. So ID equals VPS divide R minus VD divide R. You know, guys, there is an equation for ID. ID is a regular diode, the same as the BN junction diode. So in this case, we can say also ID also equals IS times E to power VD over VT minus 1. Now we can solve the two equations together. So multiply I or make these two equations equal together, 1 equal 2. So we can end up with VPS, or let's substitute, guys, I here in this relation. So VPS equals I times R, so IS times R times E to power VD divide VT. Here we consider N equals 1 minus 1, then plus VD, the remainder term we have here. So this is the loop of our volt here. Now, guys, this equation is a nonlinear equation because, as you can see, we have exponential parts here. And it's not easy to be solved analytically. In order to solve it analytically, if you would like to get VD, why it's not easy, guys? Because as you can see, we have V diode here and V diode here as well. So V diode is one term of the equation and also in the power of the exponent part. So it's not easy to solve this equation to get VD if VD is not given or unknown. Okay, guys. So in order to solve this equation, we have some techniques. One of the technique is trial and error. So we can use trial and error in order to get the values of ID and VD, or I and VD. Okay. Even, sorry, I is already substituted. So we have just one equation in VD. So in order to get VD, we have here IS. IS should be given for any diode. Resistance is our load resistance. It's well known. So VT is given also 0.026. And we now need to calculate VD at a certain power supply level. So in order to get VD now, we can use trial and error in order to get the value of VD. Or another way is to use graphical way. Graphical way in order to get the value of VD. Okay. Let's solve this example together. So in this example, guys, we need to determine the diode voltage and the current for the circuit shown in figure 128. So the figure 128 actually is the same circuit we had here. So this is our circuit, and we need to calculate the I and VD in order to draw the diode characteristics. So what is given here? Here we have a certain diode, and in any diode data sheet, you will have the saturation current given. So we know that for a certain diode, we know the value of the saturation current. It's 10 to power minus 13 ampere. And we need to get a relation now. So for the circuit we have, assume that V supply is given equals 5 volts. So we have 5 volt VPS, and we need to get the different values of VD. Okay, guys. How can we do that? So if we first apply or try VD equals 0.6. So 0.6 is reasonable value because we mentioned, guys, that the diode volt of the turn on volt should be small value, correct? So apply 0.6. So if you apply this in our equation, so 2.7, the equation will be 2.7. So equation is not balanced. So if you applied VD here, In this side, the equation will not be 5, it will be 2.7 only. So this is incorrect. Increase it to 0.65. So what I'm doing now, you guys, is I'm just make trial and error. So apply different values of VD in this side on the left hand side and check sorry, in the right hand side, and check the value in the left hand side. So 0.65, so I increase the value 0.65. If you apply VD equals 0.75, you will get the left hand side equals 15.1. So it's above 5. So this means now you should try values between 0.6 and 0.65. Is it correct? So start increasing and decreasing, going back and forth until getting the left hand side equals 5. So this is called the trial and error method. Actually, if you do that, here in the textbook, he got VD equals 0.619 and the left hand side is 4.99. So this is acceptable. So we can say now this is the value of VD. Okay, which is essentially equal to the value of the left hand side as we mentioned in this equation. Then the current in this circuit, guys, can then be determined by dividing the voltage. So now you can substitute in the equation I equals V power supply minus V divide R. So R is given in this example equals 2 ohm. So 5 minus 0.619 divided 2 is 2.19 ampere. So this is the value of current in this circuit. So this is now, guys, called the operating point. This is called the operating point. Operating point means as the supply volt of 5 volt and load of 2 ohms, okay, so sorry, 2 kilo ohms. So this the current is 2.19 milliampere. For sure, if you change the voltage of the supply, if you change the resistance value, the current is going to be different. So this is here the calculation of this circuit at a certain load condition. The other solution, guys, is called graphical solution. The graphical solution actually depends on drawing two curves and getting the intersection point of the two curves. And the intersection point is called the operating point or Q point. How can we do that? Simply, if you have a look here to the equation, VPS equals IDR plus VD, this is nothing but a straight line equation. So simply, we have here our diode characteristics. So in this case, guys, in order to solve graphically, you have to have the diode characteristic from the data sheet. So here, for instance, we have the data sheet. This is the diode characteristic, and we need to know which point is the operating point. If we have the supply of 5 volt and a resistance of 2 kilo ohms. So simply, we can draw what's called load line. What's the meaning of load line? From this equation, guys, we can say ID equals VPS minus VD divide R. So this is the equation now. And we need to get the value of VD if I equals 0, and the value of I if VD equals 0, which means these points, the intersection point with the vertical and horizontal axes. So this is how can we get the load line terminals or the load line point. So at this point, for instance, guys, here we have the value of VD equals 0. So substitute here at VD equals 0 in this equation. So this means ID equals VPS divide R, and power supply is given and resistance is given. So we can say now 5 volts divide 2 kilo ampere. So the value will be, 2 kilo ohms. So the value is going to be 2.5 milliampere. So again, this operating point here, 5 volts divide 2 kilo ohms. So this is going to be 2.5 milliampere. So this is the current ID at VD equals 0. And this is going to be our first point. And since this is a straight line equation, we need just 2 points to draw this equation. So the second point can be obtained if you apply ID equals 0. So ID equals 0 means all of these lines. So the intersection with the horizontal axis will be our point here. So at ID equals 0, VPS equals VD. So the value of VD will be 5 volts. So this is the second point here. So here VD equals V power supply, which is given 5 volts. So this is going to be the second point. Now we got 2 points on the straight line equation, so we can draw this straight line, and the intersection point here will be our operating point or Q point. So graphically now we can get the value of this point by getting the vertical X value and the horizontal X value. So you will get that VD equals 0.62 ohms and ID equals 2.2 milliampere. So this is approximately the values of this operating point. So this is another technique to know the operating point of our case. Now, guys, this is just one curve. When we have a voltage of 5 volts and a resistance of 2 kilo ohms, for sure, if you have different value of volt and current, which means different value of volt and load, this will change the value of operating point. This is going to be your first assignment. I will ask you all guys to make a program on SPICE. Next lab, we will start discussing the SPICE. So in SPICE, you need to change the supply volt and resistance value and calculate or draw the characteristic of a PN diode, a PN junction diode. This will be posted on eCampus, okay? But not today, maybe by the end of this week. Okay, guys? And this is like one activity, okay? It's not a complete homework, just one activity to know how to use simulation in order to change the values and draw a characteristic of any element. Okay? Great. Now, there is one well-known model, guys, for a PN junction diode is called piecewise linear model. So what is the piecewise linear model? Let's describe it together. So the idea of the model is approximate the diode's current to voltage characteristic using linear relationship. Actually, we know that the equation of current is exponential. So exponent is not a linear relation. But can we assume the relation is linear? This is what's called piecewise linear model. So we assume as if the relation is linear in a certain parts, especially during turn on parts. Okay. So for the piecewise model, for the piecewise linear model, we assume that the diode characteristic, which is current volt characteristic, is linear relation or a straight line relation. So this means you will start at a certain point here and you will have a slope for your line. The intersection with the horizontal axis with the values of VD is called V gamma. So this is the value of the intersection with the horizontal axis. And the slope of this line equals I divide V, or let's say delta I divide delta V. So I divide V means it's 1 over resistance. So the slope here is 1 divide RF. What is RF? RF is the diode resistance. Okay, guys? So RF is the forward diode resistance. Okay? We don't care about the reverse diode resistance for the time being, because during turn off, the diode is almost open circuit. We will not care about the conduction loss. Later on, we will discuss what the meaning of losses in a diode. But we care about the diode during turn on, because the diode, when it turn on, it will have equivalent resistance, and this resistance has a current flowing on it. So by any way, guys, if you have a resistance and a current is flowing in this resistance, you will have some losses. You know that power across any resistance equals I squared times R. So we care about the resistance or the equivalent resistance during turn off. We don't care about the resistance during turn on. We don't care about the resistance during turn off. Okay, so the slope here is again is 1 over RF, and RF is called the forward diode resistance, or let's say diode resistance. Okay, and V gamma is the turn on volt, or you can say also it's cut N volt. Cut N because the conduction starts from that point. Okay, so this is called turn on volt or cut on volt. So this is the relation during turn on. During turn off, guys, we just have I drain equals minus I saturation. This is what we need in the turn off. So this is called the piecewise linear model. Where is the linearity in this model? The linearity is in the forward biasing relation. So this is called piecewise linear model. If you would like to draw the characteristic of the piecewise linear model, so we can say now, for any value of Vd greater than V gamma, you will have a current flow and in a linear relation. And if Vd is less than V gamma, the current will be the Is. But in the ideal case again, we can say if Vd is less than V gamma, I equals 0, or the diode is going to be open circuit. So this is here if Vd is less than V gamma. This is the ideal case, and Id equals 0. Okay, so this is during turn off periods. And during turn on periods, as you can see here, we will have a linear relation for our current. As you can see, one more thing, guys, regarding the ideal case. This line here seems has no slope. It's vertical line. Vertical line means 1 over R, which is the slope, equals infinity. So for this curve, you don't have a slope. So the slope actually is infinity. And this will happen if only R, for sure this is RF, if RF equals 0. So the ideal case also for a diode, in order to be a lossless diode, is RF equals 0. So this is the ideal case of the piecewise linear model, okay? Or let's say the approximation of the piecewise linear model. So RF equals 0 and Vd equals V gamma in order to turn on the diode. And during turn off, we assume that the I equals 0. Okay, so this is the equivalent circuit for a diode. Now I have a question for you guys. You need to think about it. We said that the gamma or turn on volt is around 0.4, 0.7 volts. If you have a diode with a breakdown volt of 15 volts, so 0.7 or 0.4 is relatively high compared to the 15 volts. So if I'm comparing now, if I have V gamma equals, for instance, 0.4 volts, and if the diode is V breakdown, okay, of diode equals 15 volts. So the ratio between zero point 0.4 and 15 is relatively high. It's not very small value. But if you have another power diode with the same V gamma 0.4 and the breakdown volt of this diode is 1200 volts. So in this case, for sure, we can say this volt can be neglected for the 1200. So we do prefer to use the ideal cases if you are working in high power. So if you are working in high power, I'm not going to say, yeah, the diode is going to be turned on if the V of the supply is greater than 0.4. No, I will say once V is greater than 0, the diode will be turned on, because 0.4 can be neglected for very high volt like that volt, 1200 volts. Okay, guys? Or let's say our domestic load, we have a line to neutral volt of around 115 volts. So still 0.4 compared to 115 is very minor or a small value. However, if we are using very small power diodes, which means current of this diode is in milliampere and the volt is relatively small volt, so we do prefer to make exact calculation. Okay, guys, so this is something important to you. All of you will work later on in, if you do prefer to work in design, so you have to consider this when you design anything. So if it is high power diode, you can neglect these values and assume the ideal case. But if it is light current and low voltage magnitude of diode, so you have to consider the calculations of the value of resistance and V gamma in your calculation. Okay. We have here an example. So let's see this example together, guys. In this example, guys, we need to determine the diode voltage and current in the circuit shown in figure 128. So the same figure again, 5 volt supply, 2 kilo ohms, and we have the ID here. But in a different way. What's the different way here? So we need to calculate everything using the piecewise linear mode. So we already used these values before and we calculated something, but now we will have some exact values. Like what? Like for instance, previously we didn't consider the resistance of the diode. Now we have a resistance of 10 ohms. And V gamma is given here 0.6 volts. What do we need here? We need to calculate the value of ID and VD. So simply, if you apply Kirchhoff current and voltage law here in this circuit, you will have the same relation, VPS equals ID times R plus the equivalent circuit of our diode. Now the equivalent circuit of our diode is going to be the RF in series with V gamma. So we can say now ID equals VPS minus V gamma divide R plus RF. This is the first equation I described with you from like half an hour, for instance. Okay, so here we consider the value of RF. So 5 minus 0.6, V gamma is given 0.6, divide our resistance, load resistance, 2 kilo ohms, plus 10 ohm resistance of our diode. By the way, this diode resistance is relatively high, which means this diode is very low power, and we expect to have some relatively high losses if we flow relatively high current. So this is now the value of current, 2.19 milliamperes. Now, I would like to calculate the diode volt. So simply, I can say here V diode, which is the volt across the diode here, equals I diode plus times RF plus V gamma. So VD is V gamma 0.6 volts plus ID times RF. So now substitute in the relation, we got already the value of ID. So substitute here with the value of ID, and resistance is 10 ohms. So we can get the volt 0.622 volts. So these are the values, guys, if we considered the piecewise model, we consider the resistance value and the turn on volt of the 0.6. I would like to calculate the loss of this diode now. You know, guys, power equals V times I. Power equals V times I. So simply we can say power equals ID times VD. So VD is the total volt across the diode, and ID is the current through the diode. So this is going to be now VD times ID. VD is 2.19, or sorry, ID is 2.19 milliampere. VD is 0.622 volt. So the multiplication here will be 1.36 milliwatts. So this is the amount of power. We can make like breakdown for the calculations. So we can say it's ID square times RF plus V gamma times ID, the same. So you can calculate by any way. Okay, so you can distribute from this circuit or consider the overall volt across the diode in order to calculate the losses. Okay, by the way, guys, this is called conduction loss. We have something else called switching loss, but it's a bit advanced task to be discussed now. Later on, when we open the datasheet of diodes, we will see together what the meaning of switching loss, especially when we discuss the transistors. Okay, guys, but still the diode has some switching loss as well. Okay, so this is called the conduction loss. Conduction loss means the losses on diode during turn on periods. Because as you can see, guys, we consider here the turn on period only. We didn't consider the turn off. For sure, during turn off, ideally the current is going to be zero, but we will have what's called also switching loss. Okay. Okay. For a power diode means current is high, voltage is high. Can you see, guys? This is the turn off characteristic here. The first curve here represents the turn off characteristic. So this is IF, which is the current during forward biasing. And when the diode is turned off, as you can see, it's not going to be zero and stop instantaneously. No, it will decrease, and then due to the reverse recovery, it will move like that and return back again. Here, there is another definition for the power diode. We have two parts of the time, part called TA and part called TB. And the summation of the time is called TRR, which is reverse recovery time. And we consider the end of the reverse recovery time here at a value of 25% of the maximum reverse current. Maximum reverse current, which is this value here. So this is the characteristic during turn off for a high power diode. For the volt, so during turn on, you will have a volt across the diode, which is forward volt. We already calculated that in the previous example, but for a small power diode. And during the reverse recovery period, you will have a volt like that. And after that, the volt across diode will depend on the circuit. So this doesn't mean during turn off you will have 0 volt. No, because it depends on where the diode is inserted in your circuit. Later on, when we discuss the power supply and rectifiers, we will see the voltage drop across diode during turn on and turn off. But during turn on is going to be the same for every operation. But during turn off, it will depend on the circuit configuration. So I'm gonna say here, this part here will depend on circuit topology. And later on, we will see this together, guys. Why we draw here this for a certain diode? Assume that this is small diode we have or sorry, power diode in a simple circuit like the resistance one we had. If you multiply I times V, you will see this is the relation now. So I times V during this period is going to be positive until this instant. Then it will be negative here and positive again. Why? Because the current is negative in this portion. Okay, guys? And by the end, what will be the total loss? The total loss is going to be the integration of this power, because you know, guys, now it's power versus time, which is energy. But if you'd like to get the power, you need to get the average value. So you have two ways: either to get the power by getting the average value of this curve, or make integration and then divide by time in order to get the power. Okay, so this is the power diode and the losses across the power diode. So as you could see, guys, we don't have only conduction loss, we have also switching loss. So switching loss means we are making switching between this instant to that instant. And here you have a certain amount of power. So can you see here? All of this power is called switching power or switching loss. So this should be considered also for any power electronics element or any electronic element. Okay. Nice. In the remainder time, guys, let me show you quick examples for different diodes. So the first diode we have here is called general purpose diode. So this is the symbol of this diode, and this is the shape, and this is the one you will see a lot in your life. Let me change the color of this pointer again. So this is the general purpose diode. One other diode, guys, is called Zener diode. It has a different characteristic, and we will discuss it later on. What's the difference between Zener diode and regular diode? You will find that Zener diode has different color here, and this is the cathode. And here also, this is the cathode. So the silver part here is the cathode, and the other side is the anode. Okay. We may have discrete diodes. So this is discrete diode, but this is one type of diode. It's called Schottky diode. Schottky diode is a fast diode, guys. What's the meaning of fast diode? We will discuss this later on. Okay. We have some other shapes of diodes. So we have this tunnel diode. We have LED. I think all of you are familiar with LED. So LED is nothing but light emitted diode. We have what's called photodiode. So photodiode, it will provide photons or light. We have laser diode, which will provide laser. These are some other shapes of diodes, guys. So the diode can be a disc diode like that, discrete like that. We call this power module. Okay. So we have many shapes of the power diode as well. So these are some shapes of diodes. Later on, we will discuss more about these diodes and what are the applications of each type. Diode specifications. What's the meaning of giving a specification for any element, guys? So if you would like to buy a diode from the market, how can you buy a diode? So this is called the specification. Specify the diode. So preliminary in our discussion, we mentioned that there is a current flowing in the diode. So a basic thing is we have to find the current rating. So what the maximum current that will flow in this diode in the circuit? So this is the current that we should consider. So let's say now, firstly, we should consider current. Also, we should consider the breakdown volt. What is the breakdown volt? So breakdown volt is the maximum volt, or sorry, the volt that the diode is going to be burned. So the maximum volt in the diode or in a circuit across the diode should be less than the breakdown volt. Otherwise, the diode will be burned during operation. Let's have a look to a data sheet, guys, for a certain diode here. So this is a power diode, and let me open with you the data sheet. So here, guys, we have two diodes together in the same die. Okay. As you can see here, guys, we have VRRM, which is the reverse volt. The maximum reverse volt is 1200 volts. IF, the forward current, 200 ampere, and the asterisk here means at a certain operating condition. QC is the charge of the capacitance of the diode itself. It's 644 nanocoulomb. Here we have the feature of this diode. So it's mentioned here, Gen 4 means generation 4, thin chip technology of low VF. So VF is expected to be low here. Okay. Superior figure of merit QC over IF. 100% avalanche test. What the meaning of avalanche? We will discuss the meaning of avalanche and Zener in the coming classes. Okay. Let me go with you here, guys, to the absolute and maximum ratings. So this is a very important table we need to check if you select a diode. Firstly, there is a strong relation between the operation and temperature, because we mentioned that you have losses, and these losses will affect the temperature of your element. So you have to consider having a heat sink, or the maximum temperature during operation without heat sink should be less than the maximum temperature of the diode. Otherwise, the diode will be burned. For that, guys, here we have different values of current at different temperatures. So for a volt of 1200 volts, if the temperature is 75, the current can go from 136 to 272. What's the meaning of having two different values of current here? I should mention here in the data sheet. Okay. Also, if the temperature is 100, so if it is hot than the first case, so the current should be less. If it is more hot, so the current should be more less, and so on. Also, we have what's called pulsating current or DC current. So pulsating current, it can work with higher value of current. But if it's going to work with the DC current, so it will work with low value of current. So can you see here the value of the pulsating current can be relatively high. It's 1000 ampere at 25 degrees Celsius for a time of 10 milliseconds only. But the first one here is for DC. As you can see here, it's continuous current. But here we have a current for only 10 milliseconds. Is it important, guys, to know these things? Yes, it's very important, because it depends on the application. Depends on the application. Are you going to use your diode to be on forever, or it will be just turned on for a certain period? So the same diode that can be used with 100 ampere, but for a constant current, can be used with 1000 ampere if you need to apply it for a certain period, like 10 milliseconds. Okay, guys? So the selection of the diode depends on the application. What is the application you are going to use? So we mentioned now two things, guys. The value of current and time. So we have, guys, what's called I square T, which reflects how much ampere square second you can operate your diode safely. For that, guys, we have what's called I square T value for any die for any die. Die means for any electronic or power electronic element. Okay. For instance, the I squared T of this element is 5,000. So you can calculate now how much current according to the duration of time you will operate your diode in order to keep it safe. Okay, guys. Okay, so this was a quick discussion from the data sheet. We still have a lot of things in data sheet regarding the characteristics and other mechanical characteristics also, but we can discuss this in another class. So thank you so much, and I'm just would like to remind you guys to expect the classes a bit late. So maybe around 7 or 8 p.m. the coming time. This is one thing. Another thing is we will start our lab in the next week. So the coming Monday we will start lab. So the coming Monday is gonna be week number 3, and we will start the coming lab with a tutorial. I'm gonna make a tutorial for you how to use the spice in simulation. So if you would like to work from home or use your computer anywhere, and I urge all of you guys to use your own computer in order to install the software on the computer to be used at home and make any assignments you need. Okay, so this is everything for today. Thank you so much and have a nice day.